Hello, so today I'll be going through elimination mechanisms, and more specifically is the three mechanisms E1, E2 and E1CB, which I grouped together because in my opinion they seem to be aligned along the same spectrum. So in E1, the leaving group, which is in this case this halogen atom X, leaves first, right? That's the first step. In E2, there's a concerted mechanism, right? Where both the H plus get abstracted and the leaving group leaves at the same time. And in E1CB, a H plus leaves first. So what do I actually mean? So let us first take a look at the mechanisms of these few reactions. So let us first take a look at E1. So what is the mechanism for E1 in the first step, which is the slow step, the rate determining step? We see that the leaving group leaves first, so this gives you with a positive charge on this carbon, and then after that a base comes along to abstract the hydrogen, and what do we get? Okay, so let us take a look next at the E2 mechanism to see how it differs from the E1 mechanism, right? It's actually that the base comes to deprotonate this, remove this hydrogen, and the leaving group leaves at the same time one concerted step. So we can say that rate depends on both the base and the halogenoalkane, while over here rate is just dependent on the halogenoalkane. So you will get you the same product. However, we will note that sometimes for our example in cyclic compounds, the stereochemistry may differ. Okay, so let us then take a look at E1CB. E1CB is normally only used for ketones, right? The abstraction of the H plus from the alpha carbon of the ketone, this called the alpha carbon. And so the reason for this is because the hydrogen bonded to the alpha carbon of a ketone is especially acidic. So it's possible that this deprotonation occurs first, in fact, and normally it is because a base comes in to abstract this hydrogen. This then results in, if you agree with me, this carbon ion, but there is the possibility of resonance if you agree with me, and then this can be protonated to form an enol. So this is basically the base catalyzed pathway for the ketoenol tautomerism. So if you realize, you follow with me, right? This is basically two ends of the same spectrum, if you agree. So on one end, the leaving group leaves first. On the other end, H plus leaves first. And in the middle, H plus and X minus leaves at the same time in one concerted step. So now I'd like to talk about the next point, which is elimination and substitution competition. So if you were to look at this portion over here, you realize this carbocation over here is also the same carbocation intermediate for the nucleophilic substitution of the X group with a nucleophilic reactant. So what we observe is that instead of abstracting this hydrogen over here, another possible step that could have occurred would be just the base attacking here, forming what would be SN1, such it will be like a SN1 the second step of the SN1 mechanism, right? And same thing here, this base, right, may not have actually abstracted the hydrogen, but simply have gone over here and pushed out the leaving group, thus also resulting in a substitution occurring instead of elimination. So this is why we notice that for elimination, we are using a base as the reactant. For substitution, we are using a nucleophile. So we realize that bases and nucleophiles are actually very similar, very closely similar, which is they are both electron pair donors. It's just that when you do elimination, we are talking about a bronze-stirred Lowry base. So the electron pair is donated to H+, whereas for substitution, the lone pair is donated to a C delta plus. So how do we ensure that, say, elimination occurs instead of substitution, right? There's two ways. Firstly, you use a very strong base. For example, OH minus in ethanol is a stronger base than OH minus in aqueous solution. Why? Because OH minus in aqueous solution can form very strong ion dipole interactions with water molecules. Thus, right, actually dispersing the negative charge on the OH hydroxide anion, and thus making it less strong of a base, whereas OH minus in ethanol is less tightly solvated, and thus is a stronger base. And we note that normally basic strength increases faster than nucleophilic strength. So OH minus in ethanol is a much stronger base than OH minus in aqueous solution, much more so than OH minus in ethanol is a stronger nucleophile than OH minus in aqueous solution, right? And so we can also, another way is to use a bulky base, because note that H plus is not so sterically hindered to abstract. But we note that the delta plus carbon is fairly sterically hindered. For example, a clear illustration would be this delta plus carbon is fairly hard to attack, more difficult than it is to abstract this hydrogen lying over here. So the use of a bulky base that can easily abstract this hydrogen but not so easy to attack this carbon over here would be favor elimination over substitution. For example, of a bulky base would be triethylamine, for example, or basically any tertiary amine with 3 bulky alkyl groups attached to it. Right? There are also many examples of interesting bases that can be used for such a situation. Okay, so I am actually done here with this short introduction into elimination mechanisms as well as elimination and substitution competition, and I hope this video has been useful to you. Thanks.